Chapters 7 through 11 concern lifetime data analysis. In general, you place n items on test of a particular manufactured product. In some cases, you have what is known as a complete data set. That is, you get to watch all n of the items fail and you have n lifetimes. In other applications, you get what is known as a censored data set. The illustration below shows a right-censored data set where time is measured horizontally, and 1 through 5 here represent 5 light bulbs that are placed on test, and the the horizontal lines correspond to their lifetimes. Bulb number 5 fails first, and its failure time, which is denoted by this X, is the particular value of time along that axis. The second bulb, bulb number 2, fails next, and it fails right here. And then bulb number 1 fails right here. Now at this point in the test, we can wait for bulbs 3 and 4 to fail, but that might take a long time. So oftentimes we truncate the test, and in this case we're truncating the test when the third bulb fails, and bulbs number 3 and 4 are both considered right-censored observations. We know that somewhere to the right there's going to be a failure time for both of them. We just don't happen to know what it is. The temptation might be to throw those particular lifetimes out and just use the 3 we observed, but that would throw bias into our estimation because bulbs number 3 and 4 are our 2 best bulbs. They lasted the longest, so we would be biasing low in terms of our estimate of the mean time to failure if we throw those right-censored values out. So that's Chapter 7. Chapter 8 concerns fitting parametric models to data. And parametric models are basically these probability models that were considered back in Chapter 4, such as the exponential, Weibull, log logistic, etc. The illustration below concerns fitting the Weibull distribution to n equals 23 ball-bearing failure times. On the left-hand graph, you have time on the horizontal axis and the survivor function on the vertical axis. So probability of survival goes from 0 up to 1. And the step function here is known as the empirical survivor function. Basically, all it does is take a downward step of 1/23, and more generally 1 over n, whenever it encounters one of the lifetimes. The smooth curve is the fitted Weibull distribution, and in this particular case that is fitted by maximum likelihood, and as you can see, the Weibull fitted distribution does a pretty good job of approximating the empirical survivor function. The graph on the right has lambda, which is the scale parameter on the vertical axis, and kappa, which is the shape parameter on the horizontal axis. The dot that you see in the middle there is the maximum likelihood estimator, and that is lambda hat, kappa hat. And then the guitar pick shaped region that's around it is known as a confidence region. A confidence region is the two-dimensional analog of a confidence interval, and in this particular case what is plotted here is a 95% confidence region for the parameters lambda and kappa. In Chapter 9 we consider a covariate, and we look at the Cox proportional hazards model and the accelerated life model, which were introduced back in Chapter 5. And for any t greater than 0, here is the hazard function, and here is the survivor function for those two models. In the illustration below here, we have time on the horizontal axis, the hazard function, which measures the risk on the vertical axis. There is a single covariate here, which is the turning speed, and that ranges from 1600 RPM to 2400 RPM. So you can see that turning speed, if it's on the lower side, like 1600 revolutions per minute, you're going to have less heat and therefore less risk to having the drill bit break. And if you have a higher turning speed, for example 2400 RPM, the risk is going to be higher. So these models are used for incorporating a covariate into the lifetime distribution. In Chapter 10, we consider non-parametric methods, and that is to say the parametric methods, which are using a parametric model such as the exponential distribution or the Weibull distribution, are not being used. We're going to let the data speak for itself. One of the most popular non-parametric estimators is the Kaplan-Meier product limit estimate of the survivor function. It was devised by Kaplan and Meier back in 1958. And about 10 years ago, that particular estimator was the #1 most cited statistics paper in the literature. The way the Kaplan-Meier estimate works for S of t, this solid step function here is the point estimator of the survivor function. And as you can see, it has various heights to the steps by which it decreases. Part of that is because of tide values. The other reason the height of the steps differ are these hash marks here, and those hash marks correspond to right-censored observation. So the solid curve here is our best guess for the survivor function. And the dotted lines are 95% confidence intervals. So for example, at time 11, which is right here, if I were to be asked, what is my best guess for the probability of surviving to time 11, I would give this height right here. If I wanted a 95% confidence interval for the probability of surviving to time 11, this would be my lower bound and this would be my upper bound. Finally, Chapter 11, Assessing Model Adequacy, is basically goodness of fit tests. One popular goodness of fit test is called the Kolmogorov-Smirnov goodness of fit test. And the Kolmogorov-Smirnov test statistic is the largest vertical distance between the non-parametric estimator, and this is back to the ball bearing failures again. There were 23 ball bearing failures. We watched all of them occur, which means this non-parametric estimator simply drops by 1/23 at each data value. And the smooth curve here is the exponential fit to that data set. And as you can see, this exponential fit is vastly inferior to the Weibull fit, which we saw a few slides ago. So here is the largest vertical distance between the step function and the smooth function, and that's denoted by D23. Not surprisingly, the larger you get for your test statistic, the poorer the fit, and in this case, the exponential is a bad fit. Why is it a bad fit? It's a bad fit because the exponential distribution has the memoryless property which says a used item is as good as a new item. Well, that's certainly not the case with ball bearings. With ball bearings, they are wearing out, so you would prefer to have a new ball bearing as opposed to a used ball bearing. Finally, before we finish off this chapter, keep in mind that everything we have here in terms of looking at the reliability of a manufactured item also applies to the service industry. So for example, if a Overnight package delivery company like Federal Express promises a package by 10:30. If that package doesn't make it by 10:30, that's considered a failure. If it is delivered before 10:30, that's a success. So you have data coming out of values in the service industry as well. And this same notion applies to security and a number of other applications.